Um, Hello, everybody. To those of you who are joining today, welcome. Happy Friday. My name is Kannan, and I'm one of the co-founders at Yugabyte. Pleasure to welcome you all to today's episode of the YugabyteDB Friday Tech Talk by engineers for engineers. And like Franck was just saying, this will be the last YFTT for 2023. And we'll resume again in January. But let's get started. Franck, great to have you on another episode of YFTT. So over to you.
Yeah, thank you. So yeah, quickly, I'm developer advocate at Yugabyte for more than 2 years. And my goal is to share, to help users and developers and also get feedback. That's why if people have feedback, comments about the handling of serializable errors and retry logic, either now or later on the Slack channel, it's always good to know what the users are doing with the database. That's the best way to we can improve it. So yeah, this topic, basically, let's explain serializable errors. So basically, those are errors that are kind of normal, and then the application must handle it, just because with concurrent transactions, if there are some kind of complex transaction at the same time, not all can be successful always. There are some combinations that cannot work and must be retried when the conflicts are different and gone. So if I take just a quick example, something very basical, we have a balance. We manage accounts, for example. We have a balance of $100, and user A wants to withdraw 20, and user B wants to withdraw 30. And the operation on the database are reads and writes. So they will read the current balance and write the new balance. So at the end, we know what should be the result, 50. But let's say that they do that at the same time. User A reads the balance, 100. At the same time, B reads the balance, and it's still the same because nobody changed it and no change committed. And then user A withdraw 20 and then sets the new balance to 80 and commits that. So that's perfect. The problem now is when B tries to do his withdraw 30, because he has read 100, then it tries to set 70, and that cannot work because he has read something that has changed since that, so the commit fails with a serializable error. So this is the database telling we tried to accept the transactions at the same time to be scalable, but there are some combinations that conflict. And then the application just has to retry, because retrying now B is alone, reads the new balance, 80, and can set the new balance after his withdrawal. So the problem is solved. It's an error for a transaction, but the business transaction at the end works if the application can handle this error and just retry it. And basically, it can sound annoying, but there is no choice. If we want concurrent users, those conflicts will happen, and either we avoid them by serializing the transaction one after the other, but then we have a scalability problem, but we can with locks, or we have this optimistic locking where we do not block the other, but if we detect a conflict, then the application has to retry it. And when we can, the database will retry it automatically. If it's a single statement that has sent nothing to the user, we can roll back and retry. In Yugabyte, we take an implicit save point before any statement, and then we can retry it. If it's the transaction that has done nothing, we can. But if the transaction or the statement has already sent some result to the application, we cannot, from the database point of view, roll back that because we don't know what the application has done with this result. The only thing we can do is tell the application, we need to roll back that, and then the application does the rollback and maybe does something else if they already write the result somewhere. For example, they have to cancel it. So when the database can do it, the database will do it, but there are some cases where the application has to catch the error, and this is what we will see. If you don't catch the error, then the consequence of it is that in those cases, you will send an error to the end user. For example, a web page saying, "Oh, something failed, you have to retry." And that's not the best user experience. So this is why it's better that the application handles it. Even if it's not frequent, those kind of conflicts, you don't want that for the user.
Yeah, I just wanted to maybe call out, for example, on the previous slide that essentially, even in serializable isolation mode, where you might expect that, hey, it should look like transaction 1 executed after transaction 2 or vice versa. The reality is this error happens because the databases are not trying to run all transactions in a perfectly serial mode, so sequential mode, right? For performance and throughput, these transactions run concurrently, and that's where you can get into some of these situations. So this is not, for example, specific to a particular database like MySQL or Oracle. This is a pretty common practice, a best practice to be followed to catch these serializable errors in your transactions.
Yeah.
And yeah.
Because if we truly serialize, then we are not scalable. So the idea is that we don't serialize, but we accept only transactions that could behave the same as if serialized.
Yep.
And then before looking at how to handle that on the application, just to understand the internal, what happens internally. So in YugabyteDB, if you follow the YFTT, you probably know these two layers where we have Postgres on top of distributed storage, and the transactions are handled by the distributed storage. This is how we can be resilient. And this distributed storage called DocDB. If we look quickly at the codes, the conflict is dictated by an internal error that is K conflict. There are a few transactions error code, and K conflict is one of them. And then this is sent to the SQL layer, YSQL, that is actually the gate to the Postgres code. And there, this K conflict is translated to a serialization error. So that's kind of easy. If we see a K conflict, then we raise the serialization failure error to the Postgres code. And then the Postgres code will report that as the standard SQL state for this serialization failure, Postgres compatible, so the same error message. Here is the code where we do this translation, just setting the SQL state. I don't know exactly why we do that character by character, but why not? I'm not a specialist in C++. And then this error is really the same as Postgres, the one that is documented in Postgres for the serialization failure. So this is how we detect something on the Yugabyte specific distributed transactions and get the same behavior as Postgres. There is also a file in the Postgres code that you also find in the YugabyteDB code that lists all the error codes. And you see that the transactions one are class 40. And there are two that are really interesting there, the serialization failure. So 40,001, and also the deadlocks. We will see that a bit later. So that's basically how it works internally. And if at some point the database can retry it, it will retry it. It can retry it in DocDB, it can retry it in YSQL. But if it cannot, then this SQL state is sent to the application. And to take an example of application, pgbench, that is written in C, and that's an application that is used for different tests and benchmark, shipped with Postgres or with Yugabyte. It's a YSQL bench. And the retry logic there, you just add max tries. So by default, if it gets any error, it stops the client that is connected. So here, for example, we start 10 clients, and if one receives an error, it stops, but with max tries, it will try it 10 times, and it will report the failed transactions and those that are not failed but had to be retried. We will see that a bit later. Basically, the code is also very explicit about how it is handled, just testing the SQL state. So serialization error or deadlock are the two that are handled by pgbench to be retried. Okay. Then more common Java applications. I can show an example. This is a small Java program that I did to demo the resilience and elasticity of Yugabyte. So what can happen when we have those conflicts, but also when a node fails and everything continues. So I catched a bit more of them. So basically, I catch the SQL exception. They all come as SQL exception. And I check the SQL state. I really don't remember why I used start with. I think we can use equal. I don't remember why I used start with. Maybe initially, initially I wanted to test the classes, but then the full message. But basically, in some cases, I want to stop the application with an error, but if those are serializable errors, retriable errors, then I want to retry. So I catch the same as pgbench, the serialization error and the deadlock error. I also catch because I use that to test the resilience. If I stop the node where I'm connected, I want to reconnect without raising an error, just retrying, grabbing a new connection from the pool. And this is why I also catch the connection failures, for example. So that's an example in Java. It's the code. We cannot use the same code for all applications because the retry itself depends also on what you are doing. For example, here I'm doing an exponential backoff because what we have seen in pgbench, it's just a loop. And if I come back, maybe I can show it, or we will see it in a demo later, but just showing the output from pgbench that has disappeared, sorry. Okay. Just getting back, but was somewhere, I opened too many windows.
Yeah.
Yeah, the can retry, and then there is just a loop behind. And this is why in the output we have seen that there are many retry. Usually if there is a conflict, if you expect transaction to be in milliseconds, you can retry, but wait a few milliseconds before retrying. That really depends on what you expect in the duration of the transaction. We have another example. Actually, we have many examples for all languages in the YugabyteDB samples GitHub repo, where we have many examples. Some implement a retry logic, some just say consider adding a retry logic there, catching the message. But let's take one that handles it. But I also have it will be easier to see that. This is a Spring application. I'm not a specialist in Spring, but there is a template to do exponential backoff, where you just say the interval and the retry policy. But it's the same, and the error is catched from that and retried.
Yeah, in many scenarios, exponential, especially if you're expecting high contention, then if there are 10 waiters, if all 9 of them retry, 8 of them are going to fail again. And so exponential backoff kind of is better because it dampens the load. Instead of everybody busy waiting, it kind of makes it more friendly.
Yeah, that's why, for example, here I introduced some randomness, because if they all wait on something, maybe in addition to that, we use lock. If they all wait on something, they will wake up all at the same time, and you don't want that they retry all at the same time. So good to have a retry that is within the response time that you expect, but with some randomness. Yeah. So yeah, basically it depends on the application. The general thing is exponential backoff with a maximum of tries, because you don't want to try for 2 minutes, for example. Probably in that case, better to get an error because something is really bad. So it depends on the application, but there are some things that will be always the same. Serializable error, so you can have that. You can have that mostly if you use the serializable isolation level or repeatable read. In read committed, we reduce a lot the probability of it, but we will see that there are some cases, because we are distributed in nodes that may have a clock skew, clock drift between the nodes. There are some rare cases where we cannot be sure which transaction was before the other because of this clock skew, and then we just have to retry. And there is also the case if you have an application that must be up always, never stopped, no downtime. It's possible because Yugabyte is resilient to failures. But if you have an application release that runs some DDL on the tables, there are some changes that are centralized in the catalog. And there is no magic. We cannot change the metadata when we are accessing the data. And then either we do as Postgres with exclusive locks. Then when you run a DDL, you block everything. But then if your DDL is long, you have downtime because you have blocked everybody. And we have, for the moment, we implemented only that one. We will do the lock one later. For the moment, we have an optimistic locking. If you run some DDL at the same time as a query that is using this table, for example, and it has some changes, then it will invalidate the version of the catalog, and the query that uses it will get the same, will get a retriable error, just telling them the catalog has changed. We cannot guarantee the consistency with this online change, and then just retry it. So if you have an application where you have a use case that must be always up, even when you change the schema of the database, catch the error, and then it would be good. Yeah. As we have seen in the Java code before, you may also want to retry if there is a connection failure, for example, because of course the database is resilient, but if the node you are connected to is not accessible, then there is nothing else to do than having a connection error. And you can also do the same, retry it. Just a small warning: if you get a connection error when you expected the result of a commit, then you don't know if it's committed or not. And in that case, how do you handle it? In addition to the retry logic, you have to add in the retry logic something where you can handle that. So ideally, your changes are idempotent. You can run it, and even if it runs 2 times, the result is the same. That's perfect. Or if you have integrity constraints, unique constraint, for example, if you insert a value with a unique constraint, if you try to insert it again because you didn't catch that it was already committed, you will get an error, but you will not corrupt your database.
Yeah, this is a great point, and applicable to sort of app development against any database. Like if at the commit step you have a timeout or a connection failure against any database, you cannot be sure if the database actually committed it and then you got the timeout or before, right? So that's something that either through versioning or some other check, you'd have to build the idempotency logic to decide whether to reapply the transaction or not.
And with SQL, there are many possibilities. For example, my first example where I read and then I update, I could just have updated, subtracting a value and returning, for example, a transaction ID. And then I can run it again and with a where clause where I'm sure that it will not do the same for the same transaction ID, for example, with a bit more complex SQL queries, we can be safe on that.
Yeah.
Okay, and then let's see if there are some questions, but maybe you want to see those kind of serialization error from PSQL. In PSQL, we get the error message. If you want to see the code, the SQL state, you need to set the verbosity of it. And that's what I do, just because I want to be sure that it returns the 40001 that I catch. So I've set verbosity, and you will see that when I will have some errors, I will get more information of it. Also, I've set, if I look at how I started PSQL connected to Yugabyte, I've set PG option so that I'm always in serializable. I will do all the demo with the serializable isolation level to get serializable errors. We can also check. So we have the same as Postgres, the default transaction isolation to serializable. We have added a YB effective transaction isolation level because we have some flags that may be able to change the real isolation level. Okay, let's just create a table, and I will run with 2 transactions because you cannot get a conflict with only 1 transaction. In this transaction, I just do a select, so a read. And read, do not block the other. We do not lock when we read, because that would not be very scalable. And on the other connection, where of course I see my demo table, I insert a new row. So that's okay. I select here, I inserted without committing. So I see this new row. This one has already read and didn't see the row. If now I select again, I should not see it. Well, yeah, I've committed here. I didn't begin commit. So I should see it if I run it again, except that to be serializable, I need to read the same state. If in the same transaction, I'm reading different states, then that will not be correct. And this is the error we have. So this error is a bit long. I will explain it. But the most interesting is this SQL state. This is what you catch in the application. The other message is to give more information to troubleshoot it. Because if you have this kind of error and you don't know why, because you don't have full control on your application, you will want to go to the log and really understand what was doing this other transaction. And here, it's not clearly explicit that it is a serialization error, except that it's mentioning the SQL state. And the reason is that the way we did it, here the message says, cannot find no transaction expired or aborted by a conflict. So what happens? This other transaction, when it has inserted a new row, that was successful, but in behind, it has detected that another transaction was relying on the previous state. And then to cancel this state that is not correct anymore, it has canceled the transaction. And in Serializable, we have some priority set. So doing the same, it can happen that the insert itself fails. Basically, if I deconfig, we have 2 parameters with lower bound and higher bound of priorities. In Serializable, it's one or the other that fails. If in some cases you may set the priority. I use that more to test and to have reproducible tests. So here we have seen this kind of error where the application just has to retry it. And this is mostly, yeah, sorry.
Yeah, just to complete a thought exercise. On the other hand, if the transaction on the left, suppose instead of using serializable isolation level, if it had been using, say, something like repeatable read,
yeah,
then those two selects would have succeeded against a particular snapshot because of our multi-version concurrency control. Yeah.
Yeah, because repeatable read is okay if you insert another row. You just want that what you have fetched doesn't change, but it accepts another row. With serializable, you do not accept another row. So the only thing we have there to do, if I commit, it is rollback, and we have to retry it. Looking at the time, let's see if we have question. I will run quickly pgbench to see the same, but at scale with many sessions. So here I'm initializing the pgbench table, and I will run the default pgbench workload with 10 clients. So I will have conflicts. And especially with this default pgbench that where all sessions update the accounts, but random accounts, and there are many accounts. But this also updates the same table. And here I've run it with max try. Where was that? Max try 50, and we are and with verbose mode. And then I've seen that some transactions have been retried 7 times, 18 times. So adding more latency, but finally, no errors.
So, Frank, did you say that this benchmark is not only updating the balance of specific accounts, but it's also updating a single row, which is maintaining the total balance?
Let's check the script that is run.
Basically, it's also updating a total balance across all accounts, right? And that's like
a total balance per branch, and I have only one branch. So this is done on purpose. pgbench is there. This one is not scalable at all, just to test the conflicts. If we want something that you should find in an application that is scalable, it updates here only the accounts. And if I run the same, but with this simple update that updates only that, I don't expect a lot of retries. Retries may happen, but only if 2 sessions are updating the same account, and I have a lot of accounts. I have 10 sessions, so it will be rare. We are really in the case of optimistic locking. We don't want to block because the conflict have very low probability to happen, but we still want to manage it. And if it happens, then there will be a retry. And then maybe the response time, instead of being 3 milliseconds, will be 6 milliseconds. But this will be very rare. And maybe while this is running, so here I do not expect retries, except if we are touching exactly the same account at the same time. However, as I mentioned before, if I want to do some online release for the application, and developers love that, let's simulate that just by adding a colon to the pgbench history table. And we can see that the alter table was successful. And on the application side, I got some errors. So pgbench is not showing, yeah, it is showing there. So same errors, like serializable error, because it's the same, it's DDL, but it's still optimistic locking. So each client, I have 10 clients, each one at some point received an error saying the schema has changed, and then you have to retry, and they retried only once. So each of them had to retry only once. So that was client 1 retrying once. Client 4, I don't see where are the retry, probably later, only once. Oh, some, yeah, because pgbench retries without waiting, then yeah, maybe. But that's still okay. And finally, then everything continues. So this is not an application downtime. And if you handle if you have a retry logic, this is not even a user error. This is just an internal retry. The consequence of it for the user is just that because there was a retry, if the transactions are usually 5 milliseconds, maybe it will be 10 milliseconds. And that happened just once, but you didn't stop the application to change the table.
Yeah. So online DDL and just having the best practice of coding, transaction error handling logic.
Yeah.
With your
maybe when you do application releases, you have some use cases that must always be up, but probably there are some that you can stop. You may have some background jobs that you can stop. So you don't need to add a retry logic for that on all use cases, but at least for the critical use cases, the user-facing ones where you absolutely want to have no downtime.
Wonderful.
Okay, I think we are just on time. Let's see if we have questions.
Nothing remaining. So yeah, I think
I will just show again. I think we share the slides at least on Slack, and the links in the slides. Probably the most useful ones are those in our sample applications, because there are all languages there. We have sample application in Node, in Go, in C++, in C#, in Python. Basically, it's all the same, catching SQL state that comes from the Postgres driver. If your application runs on Postgres in Serializable, then probably you already have this logic and you have nothing to change when moving to Yugabyte.
And how did you get to this page? So what was your GitHub search? Maybe you could just share that with the audience.
Yeah, we have another repository. It's not the repository where we have the code, another organization, and that's, sorry, I log in, but you don't need it. It's public. It's just because I have other access. Yeah, the repository is YugabyteDB samples. So it's not under the YugabyteDB repository where we have the database that is fully open source. We have that maintained by the DevRel team. And yeah, we have some example of different applications.
Great. Okay. Did you have anything else, Franck?
No, that's all. If there are no questions, we are just on time. Sorry, I just put that. Of course, if you have questions about it, we are on Slack, we are on the forum, we are on GitHub, we are on many social networks. So yeah, we also like to have feedback if something works. Should work the same as Postgres, but if you have something else, we can look at it if there is something to improve.
Great. Yeah, I'd like to thank everybody that joined today. Thank you very much, and see you all with another episode of YFTT in the new year. So have a great holiday season. Thank you.
Thank you very much. Bye.